So let me finish up the test review here with the capacitor circuits, the rest of chapter 18 here. So this is going to be a major problem on the test, just like the electric force or electric field problem. You're going to have a problem that's broken up into 5 or 6 parts, and it's going to involve simplifying a circuit and then working backwards to find the potential difference or charge or energy on that capacitor. So again, there is an example on the test review problems and also on the practice problems, and there's also a separate document on Blackboard that has 2 more practice problems for you to simplify circuits and work backwards. So I'm just going to go through the steps. I'm not going to do any numbers here, just to give you a basic idea of how to do this. So I'm just going to come up with a really complicated circuit here, just to show you what the steps would be. The circuit on the test would not have so many capacitors, but you would go through the same steps. So let's say there's a capacitor here, and here, and here, and here, and here. So this is your voltage. Let's say that there's 9 volts here, and here you have 5 capacitors. And it's not extremely complicated, but it has more capacitors than you're going to see. So that if you can do something like this, you can do whatever that you see on the test. So the first thing is that the capacitors need to be labeled. So I'm going to call it C1, C2, C3, C4, and C5. And most of the time you're given values for these. So the first step is to identify whether a capacitor is in series or in parallel, find the equivalent capacitance, and redraw the circuit. So you look at these and look at what's the first set of capacitors that are either in series or parallel. So C1 and C2 are your only option here. They're in parallel. So how do you know that they're in parallel? Because you might think, oh, well, there's not a direct path to the power supply here, right? Because C3 and C5 are in the way. But they're in parallel with each other because the left plate is connected to, I'm just calling it, or the top plate is connected to the top plate here. The bottom plate is connected to the bottom plate, and there is a junction here and here. And so it looks just like the circuit that we had above here, where you can see these two are in parallel with each other. There definitely has to be a junction in between them, here and here. And so we've identified these two, so you're going to want to redraw the circuit. You don't want to try to do this in your head. So the capacitors that you haven't looked at, you just redraw them. Or we haven't looked at 3, 4, and 5, so we just redraw them. And then we've said these are in parallel, so now we're simplifying them to one circuit. And then come up with some kind of name for it. I'll call it C12 because I combined 1 and 2. And then you just repeat. Now you look and say, okay, now what? Are 1, 2, and 4 in parallel? No, because C3 is in the way. But you see 1, 2, and 1, 3 are in series. So then you say, okay. And while you're doing this, you want to go ahead and find that equivalent capacitance, right? So when you found C12 here, they were in parallel, so you go to your equation sheet, you look at parallel capacitors, and it says that in parallel you add. So underneath here, you'd want to say, okay, C12 is going to be C1 plus C2. You want to actually find that number right under here. It'll make your life much easier. Don't find it here. It's easier if you draw C12 here, then you find C12, you find C12 right underneath. And then when you're redrawing the circuit again here, we didn't touch number 4 and number 5. So we said that these two were in series, so we redraw these two in series to one equivalent capacitance. We'll call it C123. And then down here we say, okay, well, C123, they were in series. This is the equation for series, so it was C12 combined with C3. And use this equation to go ahead and get a number for C13. Get that number right here. Then you keep going, and I say, okay, these two are in parallel, so I haven't touched C5 yet, but I'm going to simplify these two to this one, which I'll call C1234. They were in parallel, so I know C1234 equals C123 plus C4. And in this case, you'd have one more step. Hopefully you'd have more room on the right hand side, because it's nice to do these all in a line and it's easy to work backwards. But the last step, the last two are now in series. So this would be the final C equivalent, and you would use this equation again to find that C equivalent. So that's how you simplify the circuits, and then you need to go ahead and work backwards. So you have to find a charge and a potential difference across each capacitor as you work backwards. So depends what the question that you're being asked. So let's say that you're asked a question about what is the charge stored on C3. Let's say that's what the question is. So you must go through the whole process of simplifying and having that one C equivalent value that you solve for here. And then you need to find the charge and potential difference across each capacitor. So the C equivalent will always get the full voltage that you were given in the beginning. In that case, it was 9 volts. So you say, okay, the voltage here would be 9 volts. And you say, okay, well, I need a charge. And you're going to keep on using this equation that you have to manipulate. So if you're solving for charge, it's C times delta V. So you'd multiply these two numbers that you got right here to get this charge right here. And that's the charge on the equivalent capacitor. And then you go back. We're asked about the charge on 3, so we know that C1234 will get us to C123, which will get us to C3. So now we care about C1234. We need V and Q for this one. So you're always going to bring back one of these two variables. Which one? Well, these were in series to get to C equivalent. So you go back to your equations. When you're in series, you see that it's the charge that is the same. So that's what you're going to bring back. You're going to say, okay, that means that the charge on 1, 2, 3, 4 on this capacitor is whatever charge that I found here. And then you have to calculate delta V. Now you can say, okay, well, my delta V on this same capacitor is going to be Q over C. So you keep using this equation here that you have to manipulate, and you keep bringing back a variable. And you can see that if you do the work like this, where you solved for C1234 right here, you brought back the Q from the previous step, and then you solve for delta V1234 right here, your numbers are both right here for you to plug in. You don't have to go looking for them. And then we go back. These two were in parallel to get to this one. In parallel, the voltage is the same, so now you can say, okay, I know the voltage on 1, 2, 3 is the one I just found on 1, 2, 3, 4, because the voltage are the same when they're in parallel. And then you can calculate Q on 1, 2, 3, and you can say, okay, well, Q is going to equal C times delta V. And once again, you have the C and the delta V right here to plug in to get the Q. And finally, you'd have one more step in this case, and okay, these two were in series to get to 1, 2, 3. So the charge is the same, so Q on 3 is the same as Q on 1, 2, 3, and so that's your final answer. So that's the idea. If it asks for the energy stored in the capacitor instead of the charge or the potential difference, you're still doing these exact same steps, but then when you're going to the equation sheet, you're going to use one of these three equations here. So let's say that you were asked for the energy stored in C3. Well, you know what C3 is, you're given that value, you just found Q3. So then you would go here and you say, okay, what's an equation that has Q and C? It's this one, and then plug those numbers in here to get the energy stored. So that's everything. So I hope that this video is helpful, and good luck on the test. Post on the forum if you have any questions about anything that I just mentioned.